So now in this demonstration, I'm going to show you how to implement a simple state feedback control. Okay, so I've opened up an incomplete VI, and what I'll be showing is how to implement state feedback control for the balanced pendulum. So as discussed, this covers a lot of the same elements that we did for the servo PD control and as well as the first demonstration. Just a few of the differences is now we're using a second encoder channel. We're still converting it to an angle for both the rotary arm and the pendulum. So they're being converted to radians, and then for display they convert to degrees. Because encoder begins to measure an angle of 0 when you start the VI, we need to convert that to get the upright angle, because the control gain that we generated is based on the inverted pendulum model. So in order to do that, then you would subtract pi or 180, and we also add a mod function here to do the wrapping of plus minus 360. Then you create the state. So in the state here, the first state x1 will be is the arm or the servo position. The second state is the pendulum position, and then we have the velocities of those. Just like we did in the servo PD control example, we're using high-pass filters for those as well. So we're using basically a derivative with a low-pass filter with a cutoff of 50, which is like about 8 hertz cutoff. Now, and then on the right, you can see the motor direction convention to make sure that a positive voltage results in positive servo angle, and the rest is the same. So, so very similar to what we did in the second demo. Now, we want to add the state. So now we can begin adding the state feedback. So the first thing I'll do is add a summation block for the error. So we'll connect the state measurement to the negative terminal, and then I don't want any set point for now. So what I'll do is just put I just wanted a set point of 0. But I gotta make sure I specify a state or a vector of 4, because everything is defined that way. So I'll go to double, and then I'll just expand this to having 4 states there. There we go. So here's my set point of 0. So once again, this is the error. So that's my state error. Set point of 0, negative feedback terminal is connected to my measurement. The next step is adding the gain. So recall in the last demonstration we generated a gain using LQR, and we simulated this to make sure that it was a stable, to make sure we get a stable system. So I'm going to add that. So again, we'll go back to the simulation module and add a gain. Now we want to multiply so the gain is going to be a vector as well. So a vector times a vector, we want to get a scalar value out of that, because that's going to be your control signal. So I got to make sure I select dot product, and then I just enter the gain. That we have 3.9, about 30, and then 3 and 4.3. So there's my gain that I generated from LQR. I can connect that, and then the output of this gain should be a scalar value. Okay, so the last thing we need to do is add a switching mechanism, because I don't want the control to be on until the pendulum is within, say, plus or minus 5 or 10 degrees. So I need to add that in, that logic. So let's go to the comparisons here. So I'll add a select terminal. There we go. So you want the control signal, the balance control, to be active or true when the pendulum angle is within plus or minus 10 degrees. Let's see. So there we go. So pendulum angle up here, and then I'm just gonna put, so when this is within plus or minus 10 degrees, it'll tell me in range. So I connect that to my select item. So when it's in range, go to my balance controller. If it's not in range, then set that to zero voltage. There we go. So I can delete my 0 and just do that. So that should be okay. So so now I'll close the block diagram, and I'll run the VI, and I'm going to go ahead and test the pendulum out. So note, so as the VI starts, the pendulum is not moving or anything. It shouldn't, because I don't want the balance controller to be on right now. And when I lift it up, when it gets within the plus or minus 10 degree range, then the balance controller that we designed kicks in and the system is stabilized. Now it's staying within the 0 degree mark because, again, the set point is set to 0, but you could advance this and maybe like supply your own reference to the rotary arm to make this track a certain set point. And if I click on stop, then the pendulum goes down. So again, using the all the control design, the control design module, LQR, VI, we've designed a gain, we simulated the gain. I showed you how to implement a simple state feedback balance controller and confirm that that gain in fact works on the actual system. So I think a natural extension to the balance controller is people often want to do the swing up control of the pendulum, another popular experiment to be done. So that's what I'll show you in this VI. So here's the swing up VI that is supplied with our pendulum system. So it's based on a paper. I'm just going to bring up the research paper it was based on. So this is a very popular paper written by Professor Ostrom and Professor Ferruta. So it's swing out the pendulum by energy control. And this is the paper we use to implement the algorithm. So it's an energy-based controller, as the title says. It also uses the nonlinear dynamics of the pendulum system. So using that is basically giving an energy set point to the pendulum and then brings it up that way. So this is so I encourage you to definitely look up this paper and read it, and that's what we've implemented in the LabVIEW VI. So you can see we're using a mixture of classic VI, native blocks and VIs in the LabVIEW environment, as well as the formula node. So the formula node is used to calculate the pendulum energy, both potential and kinetic, and then this passes through converter to acceleration and so forth. So now this whole code here is just adding to what we did in the previous demo, which was the balance controller. So the only difference is instead of setting 0, instead of 0 we have the swing up control being connected here. So when we start up this VI and the downward pendulum, it's going to activate the swing up control. And then once it gets within a plus or minus 10 degree range, just like as done before, it switches to our balance controller. So let's go ahead and run that system. So I'm going to go back to the front panel and run the VI. So as you can see here. So once again, so swing up on the bottom. Once it reaches the threshold of plus minus 10 degrees, it switches to the balance controller. And there's a few settings here, like Umax is the maximum acceleration, mu is the actual control gain, which is pretty much the only thing you have to tune. And the energy reference, 0.42, refers to the energy required to bring it to the vertical position, which is just the potential energy of the pendulum. So if I stop it, then the pendulum will go down. And that concludes the entire demonstration. So thank you.